Run. Whoops. So where can we take this? Where can we take this? Well, we could create something that is aware of how many like neighbors it has of the same color, and maybe that will create like if there's more neighbors, it will eat like it will grow larger faster, so that we like maybe we'll lose some of these little pockets of stranded color. So let's try something like that. Let me show you something else first. So let's load this other program. Grab neighboring pixels with a for loop. So this is oh my god, I never saved this. Oh my god. No, do not. Okay. Save pixels. What, really? No, pixels 2, 4. Oh boy, okay. Don't overwrite your work, kids. Okay, now I can load. Grab neighboring pixels with A4. Let's run this guy. So here we have a little area where you can see 3 pixels, and the application of the sine and cosine to select the neighboring pixels within the coordinate system. And the numbers on the left are the actual relative coordinates of the sine and cosine of each of the pixels that were drawn on the screen. And they're actually drawn 3 away. So let's put it on 1 away. So now you'll notice they kind of like tightened up over here. So this is how we can like set up our code to check the pixels that are around. So a given pixel. So x of 105 and y of 96 and distance of 1. So I'm clearing the screen, painting it white, and I'm poking only ordinal directions for that first demo. So I'm setting the pixel xy 12. 12 is, what is 12? 12 is blue, right? So like the first one that I'm drawing is the blue one. And I'm creating a for loop, and I'm using the arc, right? So that's my angle. I just called it arc of, I'm starting with 0. I'm going to 0.75, and I'm going to increase it by quarters. So this is the first part where the sine and the cosine in Pico-8 kind of like step away from how these work in math. If this is your first time encountering sines and cosines, worry not. They're just a way for extracting coordinate information based on an angle. But what's funky about Pico-8 angles is that a full circle is 1. So instead of like 360 or 2 pi or whatever, like it is 1. So an angle of 0.25 is a like 90-degree angle because it's a quarter turn. So I'm increasing arc by a quarter turn up to like 3/4, so that I can select this one, this one, this one, this one. And actually, if you run it, you will see that the first number is 0, 1. So like it starts up above, and then it goes counterclockwise. So that's also kind of funky, but there it is. So those are the things that you need to remember. So we are setting the sine of arc times distance plus x, so that we could this moves our like point of reference a distance away from our x coordinate, and this one moves relative to this angle and this distance away from a y coordinate, our point of inquiry. And so I am setting this pixel orange, and then I'm printing the sine of arc and the cosine of arc in the top left corner of the screen. Notice here that I'm using this funky double dot and then this string of a comma and then this funky double dot. What this double dot means is that I am stitching together these values as a string of text. It is super handy when you're debugging stuff like I'm doing here. I'm using the print function to write something on the screen, and I'm writing just this number, and then I'm writing a comma, and then I'm writing this other number. And the last color that number like had was the color of the actual pixels. So you can see where the orange pixels are. Those are the coordinates over here. And similarly, it's super easy to grab all 8 neighboring pixels around a pixel. You just have to like adjust what your circle means so that you can grab all 8 eighths of a circle without overlapping and doing another like circle around. And one funky thing I noticed is that in this case, you have to add a half point to your pixel coordinates because if you don't, it looks a little wobbly. So let me just delete it here and show you. Notice how the pink one just kind of like swallowed so this is with, this is with, and the other one was without. So it kind of like needs this extra half to just make sure that you're forcing it to like be grabbing the very center of your pixel, not the top left corner of your pixel when calculating distances. So that's like a weird little like hack to just make sure that the coordinates it grabs are correct. And then you can also like combine these numbers to just force it to grab only the diagonal pixels, right? Using again the sine and cosine, and that's this like red pixel with the sort of purpley gray diagonals marked. And so that's a little aside about sine. So let's grab one of these dudes. Let's check. You know, I'm just gonna steal from my past self. I'm just gonna wholesale copy this piece of code, and what did I save it? Matrixels 4. All right, there we go. Yeah, whatever. Okay, bam. So where I'm gonna plop this? Here, right? So this is where we are drawing our circle. Let's before we draw the circle, make some decisions. So I'm gonna paste it in here. Let me adjust this. So this. All right. So I don't actually need this print business. This is just for my debugging purposes. So I'm going to delete that line. And I'm not going to set the pixel color anything. I want to check to see how many of the 8 neighbors are the same color. So what I'm going to do is I'm going to create a local variable in here. Let's call it neg C for neighbor color. Nay. And then make another one, local count. This is too long. Nays. All right. So we're going to start with 0 nays. And then we're going to start with color, whatever. This can be whatever it wants to be. I'm not going to say equals anything. It's going to be nil for the time being until we define it over here. And we're going to define it here. We're going to get neighbor C, and I'm going to is equal to p get. So I'm going to pixel get the, oh, we don't have the arc. It's not an arc. Oh, it is an arc because I grabbed the whole, it is the arc. I grabbed the arc. I'm defining the arc. We do not have a distance because it was just one. So we're grabbing the immediate neighboring pixel, so we don't need the distance. And x plus half, sure. And so let's remove this distance here. Plus y plus half. And I'm not painting it this color. I am not painting it any color because I'm not painting it. I am grabbing the pixel. So I cleaned up my borrowed code. So I'm grabbing the neighbor color, and I'm not yet increasing the nays. So here we will make some choices. So inside of this for loop, I'm going to create an if statement. So if nay c is c, then end. So I'm checking to see if the neighbor's color, which is this one we've created here, is equal to C, which is the color of that we've grabbed earlier in our exploration, and we've concluded that C is not white. Therefore, it is going to be some color. We're counting all the neighbors that are the same color, and so we're going to put negs plus equal 1. So this is a very handy thing in programming. If you want to increase a value by 1, you use this plus equal sign. You can also use minus equal sign. So we've created a neighbor counter right now. So it's going to calculate how many neighbors this guy has of the same color. So if it has 4 neighbors that are the same color, that's about half, right? If it has none, that means that it's a lone pixel in the middle of nowhere, and it should probably grow by a little bit. So that should be 1. So if the neighbors is 0, then it definitely needs to be 1. But if neighbors is, so okay, there's a possible 8. So let's do 1 plus nays divided by 2. So just like in math, certain mathematical operations take precedence. So when you write an expression 1 plus nays divided by 2, the first thing that the computer is going to calculate is nays divided by 2, and then it's going to add 1 to that. So let's see what this looks like. Let's run this guy. Whoa, hella fast. Too fast. Okay, let's slow it down. Let's scroll all the way to the top of the draw. Let's not do 500. That's crazy. Let's do 20. Because now it's going to be a little bit slower. But once it's picking on, once blobs get big, then they will like overwhelm everything. So maybe the radius is way too big at radius. Where is our radius? Radius of how many neighbors divided by 2. How about divided by 3? How does that look? I mean, I don't know what these numbers are going to do. I'm just trying them out and see what feels good. This is fun. You get to like root for a certain color. I feel like I like this speed. This is a good speed. Sometimes it moves slowly, sometimes it moves fast when it swallows other colors. I like the resolution too. It's like these curved growths. It just grows in little dots, little stipples. All right, so that's cool. How about if So okay, we're drawing a circle. If okay, so here's the thing. If the the pixel that is selected has 8 neighbors, so let's create another condition. If nays is bigger than 7, let's just try to be coy about this. This is bigger than 6. Bigger than 7. Then we are going to print one of these special characters that I like, which is not R, it's E. And we're going to print it at the x, y coordinate in whatever color we are printing everything, right? So let me outline here what these guys are. So Quartiop as def and these correspond to all right. I'm going to hide this in a comment, a multi-line comment this time, for your future reference. So E, I want this like noisy pattern to be printed at the XY coordinate. This will print it a little bit to the bottom and to the right than what I want to print it at. So I am going to subtract some values. I'm just going to subtract 3 here. And I played around earlier and I know that I want to negative random 4, that I feel like that looks good. So let's run this guy. So now we should get some like splotches, some little like edge cases. It's not happening as often as I would like it to. You know what's going on? It is printing this, but then it's also printing the circle fill, which is covering it up. So what we need to do is make sure that if nays are bigger than 7, then print this. But then otherwise, so if nays are less than or equal to 7, we will draw a circle. So I'm going to remove this end and actually put it here. I'm going to put an else in here. So now we actually have a 2-part if. We have if nays is bigger than 7, then print this noise pattern. Otherwise, print a circle that is this size. So this will allow us to see these dots a little bit better. Let's try that again. There we go, that's nice. So if it accidentally selects a pixel that is completely surrounded by others of its kind, it is going to drop these dots. All right, this is taking forever. Let's make it so that we can tweak our speed of growth. So this is a cool trick. Over here, we're grabbing 20 pixels every single frame. We have figured out before that we can increase this number. But how about we make it a variable? So grabbing, and over here, grabbing is equal to 20. So now I can do this. I can run this, decide that it's too slow, escape, say grabbing is now going to be 200, hit enter, resume, and now grabbing is going to keep trucking at a ridiculous rate. Because we're interrupting a program and it keeps it remembers what just happened like a second ago, we can change values that the program is currently like taking a snapshot of and continue running with a variation just to try something out. It's very handy when you're debugging to be able to do stuff like that. I like how it like takes the black cursor zone. And so this is what we've got here. We have an interesting growing bacteria petri dish ecosystem simulation. We can still throw bleach at it.